An interstellar visitor has emerged from behind our star, fundamentally transformed, and is currently displaying characteristics that astronomers insist simply should not exist, at least according to everything we previously thought we understood regarding cometary behavior. This is not merely an active comet. Shutterstock. It is a cosmic enigma that has effectively rewritten the rulebook on how objects from beyond our solar system interact with our Sun. On November the 10th, 2025, the Virtual Telescope project captured images that stopped researchers mid-sentence. These images showed a complex, structured ion tail streaming from 3I Atlas that simply was not visible just a few days prior. And here is exactly what makes this scenario impossible. The comet should have looked essentially the same, emerging from perihelion as it did approaching it. Perhaps it should have been a bit more active, certainly brighter, but not transformed into something that challenges the models we have spent decades perfecting. Yet, the data does not lie. Something profound happened during those critical days when 3I Atlas passed closest to the Sun, hidden from our view by the intense solar glare. And what came out the other side is not quite what went in. Think about that for a moment. We are tracking an object that traveled light years through the frozen darkness of interstellar space. This is an ancient visitor from another star system, entirely. And in the brief weeks it spent in the embrace of our Sun, it changed in ways we are still trying to explain. The transformation is not subtle. It is not a matter of degree. When you compare the observations from late October to what Gianluca Masi and his team at the Virtual Telescope project documented on November the 10th, you are looking at what appears to be a different object entirely, at least in terms of its observable characteristics. The ion tail that now dominates the images, with its intricate streamers and curved architecture responding to solar wind pressure, was geometrically impossible to observe during the comet's closest approach. The viewing angle was wrong. The tail was pointing away from us, hidden behind the nucleus and the dense coma of gas and dust that envelops the icy core. We knew the tail probably existed. Theory demanded it. The fundamental physics of comets in the inner solar system dictates gas emission. But we could not see it, until suddenly, we could. This is not historical astronomy. This is happening right now as you are listening to these words, and the data is still coming in. The timeline matters here. Let us establish exactly what we are dealing with. 3I Atlas reached perihelion, its closest point to the Sun, on October the 30th, 2025. For several days before and after that date, the comet was essentially unobservable from Earth because it was positioned too close to the Sun in our sky. Solar glare drowns out everything in that region. Ground-based telescopes cannot point that close to the Sun without risking damage, and certainly cannot see faint cometary features against that overwhelming brightness. We did, however, have space-based assets watching. Coronagraphs on satellites like SOHO, Stereo A, and GOES-19 are specifically designed to block the light of the Sun and observe the corona and objects passing through that region. These instruments captured 3I Atlas during perihelion, offering a crucial, if limited, glimpse of its activity when Earth was blind. But from the surface of the Earth, we were indeed blind. The comet disappeared into the solar glare in late October and did not emerge into the observable morning sky until early November. November the 5th marked the first post-perihelion observations as the comet moved far enough from the position of the Sun in our sky to be detected again. Even then, the viewing conditions were challenging, with low-altitude twilight interference. The comet was still relatively close to the solar glare, but observers immediately noticed something. The comet had changed. Reports started circulating through astronomical networks and social media that 3I Atlas looked different. Some claimed it had lost its tail, which, as we will discover, is a fundamental misunderstanding of what actually occurred. Others noted unexpected brightness levels, or a distinct lack thereof, depending on their expectations and equipment. The confusion was understandable. We were seeing the comet from a completely different geometric perspective than we had in late October, and the viewing conditions were still marginal at best. Then came November the 10th. The Virtual Telescope Project, operating sophisticated robotic telescopes in Italy under the direction of astrophysicist Gianluca Massi, captured clear images showing 3I Atlas in its post-perihelion state. And there it was. The complex ion tail was fully visible, displaying the kind of detailed structure that makes astronomers simultaneously excited and puzzled. Excited because detailed structure means detailed data to analyze. Puzzled because the complexity itself demands an explanation. Most cometary ion tails are relatively straightforward. They are narrow, relatively uniform streams of ionized gas pointing away from the sun, responding to solar wind and radiation pressure. What the images from November the 10th showed was anything but straightforward. There were multiple streamers, curved features, and variations in brightness and density along the length of the tail. This is the kind of morphology that suggests either complex outgassing patterns from the nucleus or interaction with structured solar wind, or both. This level of detail in an ion tail is a Rosetta Stone, offering clues about the volatile composition of the comet and the dynamic conditions of the solar wind it is traversing. But here is what was gnawing at researchers as those images circulated through professional and amateur astronomy communities. The tail had been there all along. It had not suddenly appeared on November the 10th. It had been forming and extending throughout the approach of the comet to perihelion, growing more intense as solar heating increased, reaching maximum development during and immediately after the perihelion passage, when the comet experienced peak temperatures and maximum volatile sublimation rates. We just could not see it. Not from Earth. Not until the geometry changed enough to bring that tail into our line of sight. Understanding why requires us to think carefully about orbital mechanics and viewing angles, about the three-dimensional reality of solar system geometry that gets flattened into 2 dimensions when we observe from our single vantage point on Earth. Shutterstock. During perihelion, the ion tail of 3I Atlas was streaming away from the sun, as ion tails always do, pushed by solar wind and radiation pressure. But that tail was also pointing almost directly away from Earth because of where the comet was in its orbit relative to our position. We were looking at the tail nearly end-on, seeing it foreshortened, compressed into the glowing cloud of the coma, optically hidden behind the brighter nucleus and dust features. As the comet moved along its trajectory after perihelion, the angle changed. The geometric alignment between Earth, the Sun, and the comet shifted in a way that gradually revealed the full extent and structure of the tail. By November the 10th, that angle had opened enough for us to see what had been invisible before. Not because it did not exist, but because we were looking from the wrong direction. This geometric revelation immediately raises a more profound question, one that threads through every aspect of what we are about to explore together. If the tail was hidden by viewing geometry, what else might we have missed during those critical perihelion days? What other changes occurred when we were not watching, or could not watch, or were watching but could not properly see? Because the visibility of the tail is just the beginning. As astronomers compiled their observations from late October through early November, other anomalies began emerging from the data. Unexpected brightening rates, non-gravitational acceleration in the trajectory, spectroscopic signatures suggesting unusual composition or activity levels. Each finding is independently interesting. Together, they form a pattern that demands investigation. And that is exactly what we are going to do. We are going to examine the evidence systematically, piece by piece, building toward a comprehensive understanding of what happened to 3I Atlas during its solar encounter and what those changes reveal about the nature and origin of this interstellar visitor. We will look at orbital geometry and visibility constraints. We will analyze what the images actually show and what those features mean. We will confront the perihelion brightness surge that exceeded theoretical predictions by an astonishing margin. We will investigate the acceleration anomaly and what it implies about mass loss, an aspect that has sparked considerable debate in the scientific community. We will address the apparent paradox between calculated mass loss and observable changes, or the lack thereof according to some reports. We will explore an unexpected opportunity involving spacecraft that may have flown through the tail of the comet, potentially providing in situ data from another star system. And we will synthesize what all of this tells us about interstellar space, exoplanetary systems, and the diversity of small bodies wandering the galaxy. This is an investigation, and you are part of the team. So let us start where any good investigation begins, with establishing what we can actually observe and why those observations were so geometrically constrained. Why couldn't we see this tail during the most intense period of the solar encounter of 3I Atlas? That question seems simple on the surface, but answering it properly requires us to think in 3 dimensions and understand how viewing geometry determines what we can observe in space. The short answer is that the tail was pointing the wrong direction, away from us. But that simplification misses the deeper lesson about how orbital mechanics, solar physics, and observational constraints intersect to create what I am calling the geometry problem. Let me walk you through this step by step. Because once you grasp the geometric situation, everything else about the post-perihelion physics of 3I Atlas falls into place. Ion tails always point directly away from the sun. They are not like dust tails, which can curve along the orbital path of the comet due to the ballistic trajectories of the particles and radiation pressure effects. Ion tails are thin, straight structures formed by ionized molecules, water ions, carbon monoxide ions, carbon dioxide ions, that are picked up by the solar wind and carried directly away from the sun at speeds reaching hundreds of kilometers per second. The solar wind is a supersonic flow of charged particles, primarily electrons and protons, constantly streaming outward from the sun in all directions. It carries its own embedded magnetic field, a frozen-in flux of magnetic energy. When those solar wind particles interact with cometary ions through these magnetic fields, they sweep the ions straight back, creating the characteristic blue-green glow of ion tails that we see in images. These interactions are not gentle. They are like a cosmic broom sweeping the exhalations of the comet directly outwards. At the position of the comet on October the 29th, 2025, at perihelion, 3I Atlas was at 1.36 astronomical units from the Sun, roughly 203 million kilometers, placing it between the orbits of Earth and Mars. At that moment, from the perspective of Earth, the comet was nearly on the opposite side of the Sun from us, though not directly behind it, or we would not have seen it at all. The geometric configuration was such that when we looked toward 3I Atlas, we were looking in roughly the same direction as the ion tail of the comet was pointing. Think about this carefully. The tail points away from the Sun. Earth was on one side of the Sun. 3I Atlas was on the other side, moving past Perihelion. When you draw a line from the Sun through 3I Atlas extending into space, that line represents the direction of the tail. And we were viewing the comet from a direction nearly along that line. Here is where a simple analogy becomes useful. Imagine you are standing behind a car at night, watching it drive directly away from you. You can see the body of the car, maybe the rear window if it is lit, but you absolutely cannot see the headlights. They are pointing forward, away from you, blocked by the structure of the car itself. Now, imagine that car turns, gradually changing its angle relative to your position. As it turns, more of its side becomes visible, and eventually, you can see the glow of the headlights illuminating the road ahead. Even though you are still behind the vehicle, that geometric change does not mean the headlights suddenly turned on. They were on the entire time. You just could not see them until the angle shifted. That is precisely what happened with the ion tail of 3I Atlas during perihelion. And for several days afterward, we were looking at the comet from a direction that placed the tail directly away from us, optically hidden behind the bright coma and nucleus. The nucleus itself, though small, probably only a few kilometers across based on brightness and activity estimates, is surrounded by a massive cloud of gas and dust called the coma, which can extend hundreds of thousands of kilometers in all directions. When you are looking at a comet nearly tail-on, what you see is that enormous glowing coma with the tail compressed behind it, invisible against the brighter foreground material. As the comet moved along its post-perihelion trajectory through early November, the geometric situation evolved rapidly. The orbital path of 3I Atlas was carrying it away from the Sun, yes, but also moving it to a position where the perspective from Earth changed significantly. The angle between our line of sight and the Sun-comet tail alignment opened up progressively. By November the 5th, when the first post-perihelion ground-based observations became possible again, that angle had shifted enough that observers could detect tail material. The reports from that date suggest it was still not prominently displayed. By November the 10th, when the Virtual Telescope project captured their detailed images, the angle had opened substantially. We were no longer looking nearly tail-on, but rather seeing the comet from an oblique angle that revealed the full extent and structure of the tail extending away from the nucleus. The observations from earlier in the approach of 3I Atlas support this interpretation completely. Back in July and August of 2025, when the comet was still outbound from its previous distance and approaching the inner solar system, observers with major telescopes documented a growing ion tail. The Hubble Space Telescope imaged 3I Atlas multiple times, capturing beautiful images showing the developing tail structure as the comet became more active approaching the Sun. The Gemini South Observatory in Chile contributed high-resolution observations tracking the evolution of the tail. Those observations occurred when the viewing geometry was favorable. We were looking at the comet from an angle that clearly displayed the tail. Then, as the comet approached perihelion and the geometric configuration changed, that clear view disappeared. Not because the tail stopped forming, not because activity decreased. Quite the opposite. Activity increased dramatically near perihelion. But because the viewing angle became increasingly unfavorable, compressing our view of the tail until it effectively vanished from the perspective of Earth. Space-based coronagraphs maintained observation through the perihelion period precisely because they could observe close to the Sun, where ground-based telescopes cannot. Instruments like SOHO's LASCO C3, Stereo A's coronagraph suite, and GOES 19's CC1 tracked 3I Atlas through late October and early November, documenting its passage through perihelion from their vantage points in space. These observations confirmed that the comet remained active, that material continued streaming away from the nucleus, and that the fundamental cometary processes were operating as expected. But even these instruments were seeing the comet from geometric perspectives that did not necessarily provide the clear tail views that became possible once Earth-based observatories could observe again from their different vantage point. Understanding this geometry problem is absolutely critical before we proceed, because it explains the apparent disappearance and reappearance of the tail without invoking any mysterious physics or unusual cometary behavior. The tail did not vanish and then reform. It was there continuously, hidden by viewing geometry, and then revealed as that geometry changed. But this geometric understanding, while it resolves one mystery, simultaneously sets up a deeper question. If we now have a clear view of the tail and can analyze its structure in detail, what does that structure tell us about what was actually happening to the comet during perihelion? Because, as we are about to see, the tail that became visible carries evidence of extraordinary activity, complex outgassing, and phenomena that pushed the boundaries of typical cometary behavior. Let me show you what the instruments actually detected. The images from November the 10th from the Virtual Telescope project are not just aesthetically striking. They are data-rich documents that reveal specific physical processes occurring within and around 3I Atlas. When Gianluca Massi's robotic telescopes captured those frames, they recorded light that had traveled from the comet to Earth, carrying information encoded in brightness patterns, spatial distributions, and spectral characteristics. Our job now is to decode that information and understand what it tells us about the state of the comet. The first thing that jumps out in the images is the word astronomers kept using: complex. The ion tail displays what researchers describe as complex morphology, meaning its structure shows multiple features, variations, and detailed organization rather than being a simple, uniform stream. Look closely at processed versions of these images, and you can distinguish individual streamers within the overall tail structure. Narrow, semi-parallel filaments extending away from the nucleus, each potentially representing a distinct outgassing source or a response to structured solar wind flow. It is like watching countless microscopic rockets firing, each creating its own exhaust trail, all being swept back by the solar wind. The tail is not perfectly straight either. It shows gentle curvature responding to the balance between radial solar wind pressure pushing directly outward and the transverse component of the magnetic field of the wind creating slight lateral forces. This delicate interplay between the emissions of the comet and the omnipresent plasma environment of the Sun is a complex dance captured in the subtle twists and turns of the tail. Some regions of the tail appear brighter than others, suggesting variations in ion density or composition that create differential light emission. Near the nucleus, where the tail originates, the structure is densest and brightest. Then it gradually fans out and dims with distance as the ions disperse and the column density decreases. This complexity is notable because not all cometary ion tails look this way. Many comets, particularly less active ones, or those observed at greater distances, display relatively simple ion tails. Narrow, fairly uniform structures without much internal variation. The fact that the tail of 3I Atlas shows this level of detail suggests intense activity creating variable outgassing or interaction with solar wind that is structured rather than smooth, or most likely, both. Such detailed morphology is a rare treat for scientists, akin to seeing the internal mechanics of a clock rather than just its face. Ion tails form when solar ultraviolet radiation ionizes the neutral gas molecules escaping from the nucleus of the comet. Water vapor, carbon monoxide, carbon dioxide, and other volatiles sublimate from the icy nucleus. As solar heating increases, these molecules stream away into the coma, where solar ultraviolet light strips electrons from them, creating ions. The solar wind, which carries its own embedded magnetic field, then picks up these ions and accelerates them to hundreds of kilometers per second, sweeping them away from the sun. The blue-green color characteristic of ion tails comes from specific emission lines, fluorescence from ionized molecules excited by solar radiation. Carbon monoxide ions, CaO+, water ions, H2O+, and other species emit light at particular wavelengths in the blue and green portions of the spectrum when their electrons transition between energy levels. That is why ion tails photograph as blue-green structures, distinct from the yellowish or white dust tails that some comets display. The color itself is a diagnostic. It tells us we are seeing ionized gas rather than reflected sunlight from dust particles. The curvature and streaming patterns visible in the November the 10th images tell us about solar wind conditions. The solar wind is not perfectly smooth or steady. It carries turbulence, density variations, and structured magnetic fields that create a complex environment for cometary ions. When the wind encounters a comet, it does not flow uniformly around it. Instead, the wind drapes around the obstacle created by the ionosphere and coma of the comet, creating what is called an induced magnetosphere, a cavity carved out of the solar wind flow by the pressure of cometary gas. The boundary of this cavity is not smooth. It waves and ripples in response to wind variations. Ions escaping from the nucleus get caught in these structured flow patterns, creating the streamers and variations we observe in detailed images. Now, let us expand our perspective to include what space-based instruments observed during the period when Earth-based telescopes could not effectively see the comet. The coronagraph data from SOHO, Stereo, and GOES 19 provided continuous coverage through Perihelion, capturing 3I Atlas against the backdrop of the inner corona and K corona brightness. These instruments block the bright solar disk with an occulting disk, allowing them to image the faint corona and objects passing through that region. The data they collected confirmed several critical points. First, the comet survived perihelion intact. There was no catastrophic fragmentation or disintegration event. Some comets, particularly those experiencing their first close solar approach, break apart under tidal stress or thermal shock near perihelion. 3I Atlas remained a coherent object, a testament to its structural integrity, whether intrinsic or acquired during its interstellar voyage. Second, the comet exhibited strong activity throughout the perihelion passage. The coronagraph images show prominent tail material streaming away from the nucleus, confirming that outgassing was vigorous and continuous. Particularly interesting were the observations from SOHO's LASCO C3 coronagraph, which has the widest field of view among these instruments and captured the tail of 3I Atlas extending across significant angular distances. Sequential images from late October through early November documented how the orientation of the tail changed, not because the tail itself was rotating, but because the position of the comet relative to the observer was changing continuously as both the spacecraft and the comet moved along their respective paths. These space-based observations complemented the ground-based data by filling in the observational gap, ensuring we have a relatively complete timeline of the behavior of the comet through the perihelion period. What we are seeing in all these images, both space-based and ground-based, is evidence of a highly active interstellar comet responding vigorously to solar heating. The intensity of that response, however, surprised researchers in ways we need to examine carefully. When you track the brightness of the comet through the perihelion period using the space-based observations, a striking pattern emerges. The comet brightened much more rapidly approaching perihelion than standard cometary models predicted. This brings us to one of the central puzzles that astronomers have been wrestling with since the data started coming in. Why did 3I Atlas brighten so dramatically? And what does that tell us about its composition and structure, perhaps hinting at its origins in a distant star system? Before we dive into the brightness anomaly, there is one more aspect of the visual observations worth noting. Several reports from early November claimed that the tail had disappeared, or that the comet looked dramatically different in a way that suggested structural changes. As we will explore shortly, these reports reflect genuine observational changes, but not the interpretation initially attached to them. The tail did not disappear in the sense of ceasing to exist, or the comet suddenly stopping its activity. What changed was visibility, partly due to the geometric factors we have already discussed, and partly due to brightness levels and observational thresholds that determine what amateur instruments can detect under various viewing conditions. Professional facilities continued tracking tail material throughout this period. But for smaller telescopes and visual observers, the appearance of the comet shifted enough to generate confusion. That confusion is understandable and actually reveals important lessons about how we observe and interpret cometary behavior. But it also led to some misleading claims circulating through social media and less careful news coverage, claims we will need to address directly when we get to the mass loss discussion. For now, the key takeaway from the imaging data is this. 3I Atlas displayed a complex, structured ion tail indicative of vigorous activity and significant outgassing. The morphology of the tail suggests either variable outgassing from the nucleus, creating multiple emission sources, or interaction with structured solar wind flow, or most likely, both operating simultaneously. The tail was present throughout the perihelion period, but only became clearly visible from Earth once the viewing geometry shifted after early November. And the overall activity level suggested by this prominent tail structure sets the stage for understanding why researchers detected such unusual brightness behavior and trajectory anomalies in the data. Because active comets do more than just produce pretty tails. They lose mass, they change trajectories, they reveal their internal composition through the patterns of their outgassing. And as we are about to see, what 3I Atlas revealed about itself challenges some comfortable assumptions about how interstellar comets should behave. Now, we need to talk about what happened to the brightness of 3I Atlas as it approached the Sun. Because this is where observations started deviating significantly from theoretical predictions. When astronomers track the brightness of a comet over time, they are not just collecting aesthetic data. They are measuring the intensity of light production, which directly correlates to activity levels, gas and dust production rates, and ultimately to the physics of how solar heating drives volatile sublimation from the nucleus. Brightness measurements combined with distance from the Sun allow researchers to characterize how responsive a particular comet is to solar heating. And 3I Atlas proved to be extraordinarily responsive in ways that demand an explanation. The standard way to characterize cometary brightness behavior is through a power law relationship between brightness and solar distance. Astronomers express this as magnitude, varying with the heliocentric distance raised to some power, written as r to some exponent. For most comets, that exponent falls somewhere between 3 and 4, meaning brightness increases roughly proportional to distance to the third or fourth power as the comet approaches the Sun. This makes physical sense. As distance decreases, solar heating increases, more volatiles sublimate, more gas and dust enter the coma, and the comet brightens. An exponent of 4 means that if you halve the distance to the Sun, brightness increases by a factor of 16, 2 to the 4th power. That is already quite significant brightness amplification for relatively modest distance changes. 3I Atlas did not follow that pattern. According to analysis by Qicheng Zhang and Carl Battams, researchers who carefully examined the space-based coronagraph photometry through Perihelion, the brightness of the comet scaled with solar distance raised to the power of 7.5. Let me emphasize what that means. An exponent of 7.5 is roughly double the typical value. And because we are dealing with exponential relationships, that seemingly modest factor of 2 difference in the exponent translates to massive differences in actual brightness changes. With an exponent of 7.5, halving the distance to the Sun increases brightness by a factor of 181. 2 to the power of 7.5. That is more than an order of magnitude brighter for the same distance change that would produce 16-fold brightening in a typical comet. This extreme responsiveness suggests something truly unique about this visitor. This extraordinary brightness response tells us something fundamental happened to 3I Atlas as it approached perihelion. The most straightforward interpretation is that the comet possesses either an unusually volatile composition that sublimates vigorously at relatively modest temperatures, or a structure that maximizes surface area and gas production efficiency, or both. Comets with higher proportions of highly volatile ices, carbon monoxide, carbon dioxide, methane, nitrogen, start outgassing at greater distances where solar heating is still relatively weak. As these supervolatiles sublimate, they can create subsurface pressure that fractures the ice matrix, exposing fresh material and accelerating the sublimation process in a feedback loop. The closer the comet gets, the more intense this process becomes, potentially explaining why brightness increased so dramatically. But there is another layer to this story that circulated widely and needs clarification. Multiple sources reported that 3I Atlas changed color during perihelion passage, becoming distinctly bluer than the Sun in spectroscopic observations. This finding spawned considerable speculation about compositional changes or surface alterations. Let me be very precise about what actually occurred here, because this is a case where accurate science got tangled with misleading interpretation. The color change reports stem from spectroscopic analysis of the light coming from 3I Atlas during perihelion. When researchers measured the spectral properties of that light, essentially breaking it down into its component wavelengths, they found that the light of the comet was bluer than pure reflected sunlight would be. Now, this does not mean the nucleus itself changed color in some dramatic way. What it means is that the light we were receiving from the comet had a higher proportion of blue wavelengths relative to red wavelengths compared to sunlight, indicating that gas emission was contributing significantly to the total light output, not just reflected sunlight from the dust. Here is the crucial distinction. Comets produce light through 2 main mechanisms. First, dust and surface materials reflect sunlight, and that reflected light is essentially the same color as sunlight, yellowish-white, what we would call solar-colored. Second, gases in the coma absorb solar ultraviolet radiation and re-emit it at specific visible wavelengths through fluorescent processes, and many of those emission lines fall in the blue and green portions of the spectrum. When a comet is relatively inactive, most of its light comes from reflected sunlight, and it looks solar-colored. When activity increases dramatically and gas production dominates, the fluorescent emission from gas becomes more significant relative to reflected sunlight. and the overall color of the comet shifts toward the blue. That is what happened to 3I Atlas near Perihelion. The gas emission contribution increased substantially due to the vigorous outgassing we have been discussing, making the integrated color bluer than it had been at greater distances when gas production was lower. Qicheng Zhang, one of the researchers analyzing this data, explicitly clarified this point in public communications, noting that the spectroscopic signature changed to show more gas emission contribution, not that the comet somehow physically transformed or altered its surface composition. This is an important correction because some media coverage and social media discussion conflated spectroscopic color with physical appearance in ways that suggested something more mysterious than what actually occurred. The comet did not turn blue. The light reaching us from the comet had a bluer spectral signature because gas emission dominated the light production near perihelion. That said, even with a proper understanding of what the color data means, it still points to unusually intense activity. For gas emission to dominate the spectroscopic signature to the degree observed requires substantial outgassing rates. The combination of the steep brightness scaling law and the blue spectroscopic signature both indicate that 3I Atlas underwent very intense volatile sublimation during perihelion passage, more intense than many comets of comparable size experienced during similar solar encounters. Why might this be the case? Several hypotheses deserve consideration. First, composition. If 3I Atlas formed in a planetary system with different volatile abundances than our solar system comets, it might carry higher proportions of the supervolatiles that sublimate most readily. Such a system could have formed in a colder, richer region of its home galaxy. Second, structure. If the nucleus has high porosity or a fluffy structure with lots of internal surface area, solar heating can penetrate more deeply and sublimate material more efficiently than in a dense, consolidated nucleus. This would maximize the reactive surface of the comet. Third, processing history. If 3I Atlas experienced minimal thermal processing during its interstellar journey because it avoided close stellar encounters after leaving its origin system, it might retain pristine, highly volatile material that solar system comets lost long ago during repeated perihelion passages. There is also the possibility that we are seeing the first perihelion passage of a previously unprocessed nucleus. Many solar system comets have orbited the Sun multiple times, and each perihelion passage removes some of the most volatile surface material, gradually creating a less responsive object. If 3I Atlas is experiencing its first ever close approach to any star in millions or billions of years, we might be observing pristine responses that long-period solar system comets no longer exhibit. This virgin comet hypothesis is particularly compelling, offering a rare glimpse into the primordial material of another star system. Whatever the underlying cause, the observational fact remains. 3I Atlas brightened dramatically through perihelion in a way that indicates exceptional activity levels. And intense activity has consequences beyond just producing impressive visual displays. When a comet sublimates material this vigorously, it is losing mass. Ice turning directly to gas that escapes into space, carrying dust particles with it through aerodynamic drag. That mass loss creates forces on the nucleus through conservation of momentum. The same principle that makes a rocket engine work. Gas jetting away from the surface in one direction pushes the nucleus in the opposite direction. If the mass loss is significant enough, these forces become detectable as changes in the trajectory of the comet, which brings us directly to one of the most significant and controversial aspects of the perihelion passage of 3I Atlas. the detection of non-gravitational acceleration in its orbit, and the extraordinary implications of what that acceleration measurement might mean for how much of the mass of the comet disappeared during its solar encounter. Here is where the story takes a turn, from interesting to potentially extraordinary. As astronomers tracked the position of 3I Atlas before and after perihelion, comparing observed locations to predicted positions based purely on gravitational forces, a discrepancy emerged. The comet was not quite where it should have been if gravity alone determined its path. The deviation was small. We are talking about positional shifts measured in arcseconds on the sky, but consistent and measurable. This is what astronomers call non-gravitational acceleration, and detecting it is not particularly surprising for an active comet. What was surprising, and what triggered intense scientific discussion and debate, was the magnitude of that acceleration and what it implies. Let me explain what non-gravitational acceleration actually means, because the term itself can be misleading. We are not talking about some exotic physics or mysterious force. The non-gravitational label simply means forces other than gravity that act on the nucleus of the comet. In virtually all cases for active comets, these forces come from the rocket effect of outgassing. Here is how it works. When ice sublimates on the nuclear surface, gas molecules escape into space carrying momentum. By Newton's third law, every action has an equal and opposite reaction. So the escaping gas pushes back on the nucleus. If outgassing occurs symmetrically from all sides equally, these pushes cancel out and produce no net force. But if outgassing is stronger from one side, say, the sunward hemisphere that receives more solar heating, or from specific active vents, then the pushes do not cancel, and there is a net force accelerating the nucleus. For 3I Atlas, the detected non-gravitational acceleration had two components. First, radial acceleration, motion directly away from the Sun, measured at approximately 1.1 times 10 to the power of -6 astronomical units per day squared. Second, transverse acceleration, motion perpendicular to the Sun-comet line, measured at roughly 3.7 times 10 to the power of -7 astronomical units per day squared. Now, those numbers look tiny, and in absolute terms, they are. An astronomical unit is the Earth-Sun distance, about 150 million kilometers. So we are talking about accelerations of roughly a millionth of an astronomical unit per second squared, about 1/10,000th of the surface gravity of Earth. But here is the thing about even tiny accelerations. Give them time, and they produce substantial effects. 3I Atlas is moving through space at tens of kilometers per second. A constant acceleration of even a few millimeters per second squared, acting continuously for days or weeks, will change that velocity by meters per second. Change the velocity by meters per second, and you change the position by thousands of kilometers over the course of weeks. That is why these accelerations become detectable. They cause the comet to arrive at positions in its orbit measurably different from where pure gravitational predictions would place it. David Farnokia, a navigation engineer at NASA's Jet Propulsion Laboratory, who specializes in computing precise trajectories for solar system objects, included non-gravitational acceleration parameters in his orbital solution for 3I Atlas, based on the astrometric data available. His calculations quantified the acceleration components I just mentioned, providing the numerical values that other researchers could then interpret in terms of physical processes. This is standard practice for active comets. Orbital solutions routinely include these terms because ignoring outgassing forces produces inaccurate predictions. What happened next is where the scientific process got interesting and the public narrative got messy. Avi Loeb, a Harvard astronomer well known for his research on interstellar objects and his willingness to consider unconventional hypotheses, published calculations relating the detected acceleration to mass loss from the nucleus. Using the rocket equation and making assumptions about the efficiency of momentum transfer from escaping gas to the nucleus, Loeb calculated that producing the observed acceleration would require 3I Atlas to lose approximately 10 to 13% of its total mass over the course of 1 month, centered on perihelion. Let that sink in for a moment. We are not talking about shedding a thin surface layer. We are talking about potentially 1/10 of the entire mass of the object ejected into space in a matter of weeks. For comparison, imagine if Earth lost 10% of its mass. That would be catastrophic. Catastrophic does not even begin to cover it. Now, comets are not gravitationally bound like planets, and mass lost through sublimation is exactly what comets do. But losing that much, that fast, is remarkable if true. It would indicate either that the nucleus was much smaller than estimates suggested, so that a given absolute mass loss represents a larger fractional loss, or that the outgassing was extraordinarily intense, or both. Loeb's calculations triggered immediate responses from other scientists, some supportive, many skeptical. The skepticism centered on several points. First, the statistical significance of the non-gravitational acceleration detection itself. While Farnokia's orbital solution included these parameters, the formal uncertainties on those parameters are substantial because the astrometric data, the positional measurements of the comet, have limited precision, especially for a fuzzy extended object rather than a point source. Some researchers argue that the acceleration detection might not be statistically robust enough to support firm conclusions without further data. Second, even if the acceleration is real, converting it to mass loss requires assumptions about outgassing geometry, gas velocity, momentum coupling efficiency, and nucleus mass, all of which carry uncertainties. Different assumptions can produce significantly different mass loss estimates. For instance, if the outgassing is highly collimated in jets, it would be more efficient at producing acceleration for a given mass loss than if it were a diffuse, uniform outflow. Third, and perhaps most telling, several astronomers examined images of 3I Atlas from before and after perihelion and reported that they could not see obvious evidence for such dramatic mass loss. The nucleus size appeared unchanged within measurement uncertainties. The overall activity level seemed consistent with a comet that had lost material, but not 10% of its entire mass. This created an apparent paradox: calculations suggesting extreme mass loss versus observations suggesting modest changes. How do you reconcile that? The scientific debate around these questions is ongoing and actually represents the research process working exactly as it should. Someone detected a signal in the data and interpreted it. Others examined those interpretations critically, pointing out uncertainties and alternative explanations. Both sides published their analyses and arguments, and the astronomy community is evaluating the evidence. This is how we advance understanding, through careful measurement, quantitative analysis, critical evaluation, and iterative refinement of hypotheses. From my perspective as someone trying to convey the current state of knowledge to you, here is what I think we can say with confidence. 3I Atlas definitely experienced non-gravitational forces during perihelion. That is essentially certain. Active comets always do. The comet lost mass through outgassing. That is also certain. You cannot have the observed activity without mass loss. The specific magnitude of that mass loss, whether it reached the extreme 10 to 13% level that Loeb calculated, or was more modest, remains genuinely uncertain and is a legitimate topic of scientific debate. The astrometric data are not precise enough, and the assumptions required to convert accelerations into mass loss are uncertain enough, that reasonable scientists can arrive at different conclusions. What makes this particularly challenging is that directly measuring the nucleus size before and after perihelion to detect shrinkage is essentially impossible with current observations. The nucleus is small, a few kilometers at most, and it is embedded in a vast coma hundreds of thousands of kilometers across. We cannot resolve the nucleus directly in images. We infer its size from overall brightness and assumptions about surface reflectivity, albedo, and those inferences have large uncertainty margins. A 10% size reduction, going from, say, a 3-kilometer diameter to 2.7 kilometers, would be very difficult to detect with confidence given those uncertainties. So we are left trying to infer mass loss from indirect evidence, trajectory changes, brightness behavior, spectroscopic signatures, all of which require modeling and assumptions. What I find particularly thought-provoking about this entire discussion is how it reveals the real challenges of studying transient events in astronomy. 3I Atlas passed through perihelion once. We will never get those observing conditions back. The comet is receding now, getting fainter as it moves away from the Sun and Earth, and it will continue fading until it becomes undetectable within months. Whatever happened during perihelion is now locked into the observational record we managed to capture during that brief window, and we are extracting every bit of information we can from that finite data set. Future observations can track how the comet continues to evolve as it moves outward, but they cannot rewind time and give us higher precision measurements during the critical period. We work with the data we have, acknowledge its limitations, and do our best to separate robust conclusions from speculative interpretations. For our purposes, the key point is this: the combination of the steep brightness law, the spectroscopic evidence for intense gas emission, and the detection of non-gravitational acceleration all point consistently toward very intense activity during the perihelion passage of 3I Atlas. Whether that activity was extreme enough to shed 10% of the nucleus mass, or was somewhat less dramatic but still significant, the comet clearly responded vigorously to solar heating. And that leads us directly into what I think is one of the most fascinating aspects of this entire story: the apparent discrepancy between theoretical expectations of dramatic mass loss and observational reports claiming the comet looks largely unchanged. Because that is not actually the paradox it appears to be, once you understand what we should and shouldn't expect to observe. Let us address the elephant in the room. If 3I Atlas potentially lost 10% of its mass, or even some significant fraction of its mass, why do some observers claim the comet looks unchanged? Why have we not seen obvious evidence in images of a dramatically smaller nucleus or missing material? This apparent contradiction has fueled confusion and led to competing narratives in public discussion. Some claiming the comet has been fundamentally altered, others insisting nothing really happened. The resolution to this paradox requires us to think carefully about what mass loss actually looks like and what kinds of changes we can realistically detect. Start with a critical distinction. When we talk about cometary mass loss, we are primarily talking about gas leaving the nucleus, not visible solid chunks breaking off. The sublimation process converts solid ice directly to gas. Water ice becomes water vapor. Frozen carbon dioxide becomes gaseous CO2, and so on. Those gas molecules escape at speeds of hundreds of meters per second, but they are invisible to optical telescopes once they leave the immediate vicinity of the nucleus. We can detect them spectroscopically by looking for their emission lines. and we can see their effects when they become ionized and form the ion tail. But the actual mass that is lost, the water molecules, CO molecules, CO2 molecules, rapidly becomes too diffuse to image directly. Think about what this means for observability. If the nucleus loses, say, 1 billion kilograms of material over a few weeks, which sounds like a lot, that material disperses into a volume of space that quickly grows to trillions of cubic kilometers. The density drops so low that the gas becomes essentially transparent and undetectable in normal imaging. The only ways we detect this escaping material are either by catching it close to the nucleus when it is still relatively concentrated, or by observing it after it has been ionized and swept into the ion tail, where solar wind compression keeps it somewhat concentrated, or by measuring its effects on the nucleus's trajectory through the non-gravitational acceleration we discussed. Now, what about dust? Comets eject dust along with gas, solid particles of rock, organic compounds, and refractory materials that were mixed with the ice. Unlike gas, dust is visible because it reflects sunlight. But here is the thing. Dust also disperses rapidly. The particles get pushed away from the nucleus by radiation pressure and by aerodynamic drag from the outflowing gas. Within hours to days, they spread into a large cloud that becomes progressively dimmer as the particles distribute across a larger area. Yes, we see dust tails on comets, but those tails represent material that has already left the nucleus and is on its way out of the system. It is not material still bound to the comet that we might count as part of its mass. This brings us to the core question. What observable changes should we expect from significant mass loss? The most direct change would be a measurable shrinkage of the nucleus itself. But as I mentioned earlier, we cannot actually resolve the nucleus in our images. It is too small and too embedded in the bright coma. We estimate nucleus size from total brightness and assumed albedo, and those estimates have uncertainty ranges that easily exceed 10%. If the nucleus shrank by 10%, going from, say, 3 kilometers diameter to 2.7 kilometers, we would have essentially no way to detect that change with certainty in the available observations. The photometric signature would be ambiguous because brightness depends on both size and activity level, and activity level was changing drastically through perihelion anyway. Another potential observable would be changes in coma morphology or dust production patterns that might indicate the nucleus lost structural integrity or altered its surface properties. Some observers would argue they have not seen such changes. The coma and dust production of the comet in post-perihelion images look qualitatively similar to pre-perihelion observations, accounting for the different viewing geometry and distance. Others would point to the complex ion tail structure as evidence of substantial outgassing and, by extension, mass loss. Both observations can be simultaneously true because they are measuring different aspects of cometary activity. Then there is the question of the visibility of the tail that we discussed earlier. Multiple reports from early November claimed the tail of the comet had disappeared, which some interpreted as evidence that activity had stopped or that the comet had fragmented or undergone some dramatic change. But we have already established that the tail visibility issues were primarily geometric. The tail was there. We just could not see it from Earth at certain viewing angles. This confusion illustrates how easily observational effects get misinterpreted as physical changes, especially in fast-moving public discourse on social media, where nuance often gets lost. Professional astronomers studying this question have offered several clarifications worth emphasizing. First, Many comets exhibit non-gravitational acceleration without displaying dramatic, obvious changes in appearance. The rocket effect can be quite efficient. Relatively modest mass loss distributed appropriately around the nucleus can produce measurable trajectory changes. You do not necessarily need 10% mass loss to explain the acceleration. Smaller amounts might suffice with the right outgassing geometry. Second, the absence of a visible tail does not mean an absence of activity. Tails are observable manifestations of activity, but they are not perfect indicators of mass loss rates. A comet can be losing substantial mass through gas emission that is too diffuse to image, while appearing to have a weak tail, simply because viewing geometry or ionization conditions do not favor tail visibility. Third, and perhaps most important, expecting to see dramatic before and after differences in the appearance of a comet from mass loss on the order of several percent to 10% is probably unrealistic given the observational constraints and the timescales involved. Think about it. The nucleus is a few kilometers across, embedded in a coma tens to hundreds of thousands of kilometers across, observed from over 100 million kilometers away. We are not looking at microscope slides here. We are trying to detect subtle changes in a barely resolved extended object against the limitations of Earth's atmosphere, telescope resolution, and detector sensitivity. The fact that professional observers do not see obvious dramatic changes does not mean those changes did not occur. It means our ability to detect them is limited by the physics of observation. So where does this leave us? The most reasonable interpretation, synthesizing the various lines of evidence and expert opinions, is that 3I Atlas definitely lost mass during perihelion. All active comets do. The specific amount remains uncertain, with estimates ranging from modest but significant up to potentially quite extreme, depending on which data you emphasize and what assumptions you make in modeling. The trajectory data suggest substantial outgassing forces. The brightness behavior and spectroscopic signatures support intense volatile sublimation. But the imaging data do not show unambiguous evidence of dramatic structural changes, which could mean either that the mass loss was on the lower end of estimates, or that our observational limits prevent us from detecting changes that actually occurred, or some combination. What is not in dispute is that 3I Atlas behaved like an active comet throughout perihelion, ejecting material into space, responding to solar heating, and displaying all the characteristics we associate with cometary activity. The magnitude of that activity, whether merely substantial or truly exceptional, is where uncertainty remains. And that uncertainty is okay. It is honest. It is what the current data support. As the comet continues to fade and recede, it is possible that continued astrometric tracking will refine the non-gravitational acceleration parameters, improving our constraints on mass loss. It is also possible that we will remain in this state of informed uncertainty, knowing something significant happened, but unable to quantify it precisely. That is astronomy. Sometimes, we work at the edge of what is detectable, and not every question gets answered with the certainty we would like. But before we close the book on the perihelion passage of 3I Atlas, there is one more unexpected development that could potentially provide entirely new data about what this comet ejected into space. Data collected not by telescopes, but by spacecraft that may have accidentally flown right through the tail of the comet. Sometimes in astronomy, you get lucky in ways you never planned. As researchers tracked 3I Atlas through its perihelion passage, someone realized that the timing and geometry created an extraordinary opportunity, or perhaps had already created one without anyone noticing in real time. The orbit of the comet, and the projected extent of its ion tail meant that two active spacecraft traveling through the inner solar system on their own missions, having nothing to do with comets, might have flown directly through the tail of 3I Atlas during the critical late October to early November period. And if they did, their instruments might have recorded data that could provide unprecedented insights into the comet's composition and outgassing behavior. The two spacecraft in question are ESA's Hera and NASA's Europa Clipper. Hera launched in October of 2024, currently en route to the binary asteroid Didymos to study the results of NASA's DART impact experiment. Europa Clipper also launched in October of 2024, beginning its years-long journey to Jupiter's moon, Europa. During late October and early November of 2025, both spacecraft were in the inner solar system, traveling along their respective trajectories toward eventual gravitational assists that would send them to their final destinations. And the ion tail of 3I Atlas, extending millions of kilometers away from the nucleus and sweeping across space as the comet moved, potentially crossed the orbital paths of both spacecraft. This prediction came from a research paper published in Research Notes of the American Astronomical Society in October of 2025 by Samuel Grant and colleagues. They calculated the projected positions of the ion tail over time, modeled where Hera and Europa Clipper would be in their orbits, and determined that the geometry suggested possible tail-crossing events. Specifically, Hera might have been immersed in the tail between October the 25th and November the 1st. Europa Clipper's potential tail-crossing window was October the 30th through November the 6th, a period that nicely brackets the perihelion date of the comet of October the 30th, when activity was at its peak. Now, let us be clear about what "might have" means here. The actual occurrence of tail crossing depends on several factors that were not known with certainty at prediction time. First, the precise width and density distribution of the ion tail. We can model this based on observed brightness and spectroscopic signatures, but there is considerable uncertainty. Ion tails are tenuous structures to begin with. Even at their densest, they contain far fewer particles per cubic meter than what we would call a vacuum on Earth. Whether a tail reaches a particular location in space depends on how extensive it is, which in turn depends on outgassing rates and solar wind conditions. Second, small uncertainties in both the comet's orbit and the spacecraft trajectories propagate over days into position uncertainties that could mean the difference between tail immersion and a near miss. But let us assume the geometry worked out, and one or both spacecraft did traverse the tail. What would that mean? Both spacecraft carry instrument suites designed for their primary missions. Hera has cameras and sensors for asteroid characterization. Europa Clipper has an extensive set of instruments for studying Europa's ice shell and potential subsurface ocean. Neither was designed to study comets. But here is the beautiful thing about spacecraft instruments. Many of them are sensitive to environmental conditions in ways that transcend their primary purposes. Magnetometers detect magnetic fields regardless of whether those fields come from asteroids, moons, or ionized cometary gas. Plasma instruments measure charged particle populations, whether they originate from solar wind, magnetospheres, or comet tails. Dust detectors count impacts, whether the particles come from interplanetary dust or cometary debris. If either spacecraft encountered the ion tail of 3I Atlas, their instruments would have recorded telltale signatures. Magnetometers might detect the draped magnetic field lines carried by solar wind through the tail. Plasma detectors would measure increases in specific ion populations: water ions, H2O+, carbon monoxide ions, CO2 ions, with abundance ratios reflecting the composition of the comet. The beauty of in situ measurements, as opposed to remote observations, is that you are directly sampling the material rather than inferring composition from spectra. You can distinguish between ions of the same element in different molecular forms. You can measure isotopic ratios. You can detect minor constituents that would be impossible to observe spectroscopically from Earth. This is exactly the kind of detailed compositional data that could tell us whether the volatile inventory of 3I Atlas resembles solar system comets or displays exotic abundances reflecting different formation conditions in its origin planetary system. This would be a scientific goldmine, providing a direct taste of an alien world. There is precedent for spacecraft tail-crossing events. NASA's International Cometary Explorer deliberately flew through the tail of Comet Giacobini-Zinner in 1985, making the first direct measurements of cometary ion tail plasma. The Ulysses spacecraft, designed to study the Sun, serendipitously crossed the ion tail of Comet Hyakutake in 1996, detecting cometary ions at distances far from the nucleus that would not have been observable remotely. More recently, several missions have benefited from chance encounters or proximity events with comets, collecting bonus data unrelated to their primary objectives. The 3I Atlas situation would fit this pattern. Opportunistic science extracted from geometric coincidence. Of course, there is an important practical question. When would we know? Spacecraft data processing is not instantaneous. Engineering telemetry gets downlinked and analyzed on relatively short timescales to ensure spacecraft health. But science data often gets processed in batches, sometimes with delays measured in weeks or months. The data containing potential cometary signals might have been recorded in late October or early November, but identifying and analyzing those signals could take considerably longer. Researchers would need to examine the instrument telemetry around the predicted crossing dates, look for anomalies or signatures consistent with cometary material, and perform the detailed analysis required to distinguish cometary ions from the normal interplanetary medium. This is not trivial work, and it is not the primary focus of either mission team, who are understandably occupied with their main objectives. So, as of now, we are in a state of expectant uncertainty. The geometry suggests tail crossing might have occurred. If it did, the data exists somewhere in the spacecraft telemetry records. Whether that data gets identified, analyzed, and published depends on whether mission team members or outside researchers take on the work of mining those archives for cometary signatures. Given the scientific interest in 3I Atlas as only the third confirmed interstellar object and the first interstellar comet to display such dramatic activity, there is certainly motivation to look. But we may be waiting months for answers. We may never know definitively if the signal was too weak or the geometry did not quite align as predicted. What I find compelling about this whole scenario is how it exemplifies the interconnected nature of solar system science. A comet from another star system passes through the inner solar system. Two spacecraft launched for completely different purposes happen to be in roughly the right place at roughly the right time. Researchers notice the geometric coincidence and make predictions. Now, we wait to see if the universe offered us a gift in the form of unexpected data. It is a reminder that discovery does not always come from carefully planned observations. Sometimes it comes from being alert to opportunities and recognizing connections that were not obvious until someone took the time to calculate the orbital geometry. And it is yet another dimension of the 3I story that keeps this investigation ongoing rather than closed. We are not done. Learning from this comet's visit. Step back with me for a moment and think about what we are actually doing here. We are studying an object that formed around a star light years away, possibly billions of years ago, and has now visited our solar system briefly before it continues on its journey through the galaxy. Every data point we collect about 3I Atlas is a data point about conditions and processes in another planetary system. A system we will likely never visit, observe directly, or even identify with certainty. This comet is, in a very real sense, a physical sample from interstellar space, carrying information about its birthplace and its journey encoded in its composition, structure, and behavior. What does that information tell us? Let us start with composition, because the unusual activity we have documented points to a specific volatile inventory. The intense brightening near perihelion, the strong spectroscopic signature of gas emission, and the vigorous outgassing required to explain non-gravitational acceleration all suggest 3I Atlas is rich in volatile ices that sublimate readily. This is not universally true of all comets. Solar system comets display a range of volatile content. Some are dominated by water ice with modest amounts of other species. Others carry substantial quantities of carbon monoxide, carbon dioxide, methane, and other supervolatiles. Where a comet forms in its planetary system influences what ices it incorporates. Objects forming closer to the star condense from warmer material with less volatile species. Objects forming far out in cold regions can incorporate the most volatile materials that condense at very low temperatures. The fact that 3I Atlas shows activity at 6.4 astronomical units from the Sun, well beyond Earth's orbit, out past Mars, and approaching the distance of Jupiter, tells us it contains volatiles that sublimate even at those relatively large distances where solar heating is weak. This strongly suggests formation in a cold environment analogous to the outer regions of our own solar system, where comets formed in the Kuiper Belt and Oort cloud. So right away, we can infer that the origin system of 3I Atlas likely had cold outer regions where icy bodies could form, which implies the presence of planets massive enough to scatter smaller bodies to large distances, probably giant planets like Jupiter and Saturn analogs. Then there is the polarization data. Earlier observations of 3I Atlas measured the polarization properties of reflected sunlight from the comet, essentially how the electric field oscillation of the light waves is oriented. Different surface materials produce different polarization signatures. Analysis of the polarization of 3I Atlas found negative polarization at certain phase angles, meaning the polarization actually had the opposite orientation from what most asteroid surfaces produce. This negative polarization is characteristic of dark, icy surfaces with mixed composition, exactly what we see in trans-Neptunian objects like Pluto and many Kuiper Belt objects. The similarity suggests the surface composition of 3I Atlas resembles these outer solar system bodies, supporting the idea of formation in a cold, distant region of its origin system, where dark organic compounds and ice mixtures are stable. Now consider the structural implications. 3I Atlas survived an interstellar journey that could have lasted millions or even billions of years, depending on how long ago it was ejected from its origin system and how fast it has been traveling. During that journey, the comet experienced exposure to cosmic radiation, occasional impacts from interstellar dust grains, and the thermal fluctuations of traveling through varying regions of the galaxy. Yet it arrived at our solar system structurally intact, not a cloud of fragments, but a coherent nucleus that behaved like a normal, if highly active, comet during perihelion passage. This tells us something about either the inherent strength of icy bodies that form in planetary systems, or about the relatively benign nature of interstellar space for objects of this size, or both. The fact that the nucleus of 3I Atlas remained intact during perihelion also provides constraints. Tidal forces from the sun, thermal stress from rapid heating, and the mechanical stress of vigorous outgassing could potentially fracture a weak or loosely bound nucleus. The comet survived these stresses, suggesting some minimal level of structural integrity. Whether this reflects primordial consolidation during formation or modification during its interstellar journey is unclear, but it is a critical data point about the physical properties of interstellar comets. Now, let us place 3I Atlas in context with the other confirmed interstellar visitors. First came Oumuamua, detected in October of 2017 as it was leaving the solar system. Oumuamua displayed highly unusual characteristics: an elongated shape inferred from its brightness variations, a relatively red color suggesting an organic-rich or weathered surface, and critically, no detectable cometary activity despite evidence of non-gravitational acceleration. The nature of Oumuamua remains controversial, with hypotheses ranging from a purely rocky asteroid object to a highly depleted comet to more exotic possibilities. Whatever it was, it clearly differed from typical solar system comets. It was a true alien. Then came 2I Borisov, discovered in August of 2019, approaching perihelion. Borisov was refreshingly normal. It looked like a comet, acted like a comet, and displayed activity and composition very similar to solar system comets. It showed gas and dust emission, developed a coma and tails, and spectroscopic observations indicated volatile composition within the range of solar system comet values. Borisov essentially taught us that at least some interstellar comets are familiar. Planetary systems produce comet-like objects similar to what our own system produced. Now, 3I Atlas is definitely a comet displaying vigorous activity and clear cometary morphology. But its behavior pushes toward the extreme end of comet activity levels. The brightness surge near perihelion, the potential for very significant mass loss, the intensity of outgassing. These characteristics suggest either unusual composition or unusual structure, or both. So we have 3 interstellar objects, and all 3 differ from each other. Oumuamua was inert and odd. Borisov was active and normal. 3I Atlas is active and intense. That is a 100% diversity rate so far. 3 objects, 3 distinct profiles. What does this diversity tell us about exoplanetary systems and small body populations? First, it confirms that planetary systems produce wide varieties of small objects, just like our solar system does. We have rocky asteroids, metallic asteroids, icy comets, mixed ice rock objects, and everything in between. Apparently, other systems do too. Second, it suggests that the formation environments and processes operating in other planetary systems can produce both familiar-looking objects and exotic ones. Borisov could have formed in our solar system and would not look unusual. Oumuamua would be strange anywhere. 3I Atlas seems like an extreme version of something familiar, a comet on steroids, you might say. Third, and perhaps most profound, this diversity tells us we cannot simply extrapolate from solar system experience when predicting what interstellar objects will look like. Every planetary system forms under slightly different conditions: different stellar mass, different metallicity in the protoplanetary disk, different arrangements of giant planets, different dynamical histories. These variations propagate into the small bodies those systems produce. Some systems might form mostly rocky objects, others might produce ice populations. Some might have intense bombardment histories that fragment and grind down their small bodies. Others might have quiescent histories preserving primordial structures. The objects that eventually get ejected into interstellar space carry the signatures of these formation and evolutionary differences. For 3I Atlas specifically, the evidence points to formation in a cold outer region of a planetary system that had giant planets capable of scattering objects, likely with a volatile, rich protoplanetary disk that allowed substantial incorporation of super-volatile ices. The structural integrity suggests some consolidation process, perhaps analogous to what produced Kuiper Belt objects in our own system. The object then got ejected, probably through gravitational interaction with a giant planet, and spent some period traveling through interstellar space before eventually encountering our Sun. We cannot determine which star 3I Atlas came from. The trajectory data are not precise enough to backtrack the orbit reliably for the thousands or millions of years required to identify a point of origin. The comet's velocity in the galactic reference frame and its incoming trajectory vector do constrain possibilities to some degree, but not uniquely. There are millions of stars within potential origin distance, and we do not have the data to distinguish between them. So the birth system of 3I Atlas remains anonymous, one of countless planetary systems orbiting stars scattered through the galaxy. But that anonymity does not diminish the value of what we have learned. We now know that at least some planetary systems produce highly active, volatile comets. We know these objects can survive interstellar journeys while retaining enough volatile material to display dramatic activity when they eventually encounter another star. We know the composition can include the kinds of ices and organic materials that make life possible: water, carbon compounds, nitrogen-bearing molecules. Every interstellar object we study expands our statistical sample of planetary system products, teaching us about the diversity of outcomes from planet formation processes. 3 objects is not much of a sample size, but it is 3 more than we had 20 years ago when interstellar objects were purely theoretical. And the next generation of survey telescopes, particularly the Vera Rubin Observatory, with its large synoptic survey telescope coming online, will likely discover interstellar objects routinely, perhaps dozens per year. Each one will add to our understanding, gradually building a comprehensive picture of what the small bodies of the galaxy look like. So, where are we now, and where do we go from here? As I am recording this, 3I Atlas is moving away from the Sun, receding from both solar heat and from the position of Earth, gradually fading as distance increases and activity declines. The comet is currently at around 1.3 astronomical units from the Sun, about the distance of Mars from the Sun, and it continues outbound on its hyperbolic trajectory that will eventually carry it back into interstellar space. Viewing conditions from Earth are actually improving now compared to the challenging geometry of early November. The comet has emerged fully from solar glare and is now visible in morning skies for Northern Hemisphere observers. Though you will need a telescope, it is far too faint for naked eye visibility and will remain so throughout the rest of its observability window. But improving viewing geometry is fighting against fading brightness. As 3I Atlas moves farther from the Sun, solar heating decreases, outgassing declines, and the comet dims. Current magnitude estimates put it around magnitude 12 to 13, which is accessible to moderate amateur telescopes under dark skies, but requires some skill to locate and observe. Over the coming weeks and months, it will continue fading as the square of its distance from both Sun and Earth. By early 2026, it will likely have faded below magnitude 15, pushing it beyond the reach of most amateur equipment and requiring substantial professional telescope time to observe effectively. By mid-2026, it may be essentially lost, too faint to track without major observatory resources, and those resources are always in high demand for many competing projects. This creates urgency for the observations that still need to happen. Astronomers studying 3I Atlas are racing against the fading light to collect as much data as possible while the comet remains observable. What are they looking for specifically? Several key observations could significantly advance our understanding. First, continued photometry to track how brightness evolves as the comet recedes. Does it follow a predictable decline based on decreasing solar heating? Or are there activity surges or sudden changes that might indicate nucleus rotation effects, exposure of fresh volatile material, or even delayed fragmentation? Brightness monitoring sounds mundane, but it is one of the most reliable ways to track overall activity levels and search for unexpected behavior. Second, spectroscopy to refine compositional measurements. Earlier spectroscopic observations focused primarily on visible wavelengths and on identifying major species during peak activity. Now, with the comet in a different activity state and different viewing geometry, additional spectroscopy could identify minor constituents, measure isotopic ratios if signals are strong enough, and track how the gas production mix changes with heliocentric distance. Different volatile species sublimate at different temperatures. So as the comet cools, moving away from the Sun, the relative abundances of different gases in the coma will shift. Tracking these shifts constrains the temperature dependence of sublimation and provides clues about ice distribution within the nucleus. Third, high-resolution imaging to monitor coma morphology and search for any evidence of structural changes. If the nucleus did lose substantial mass, or if surface features change significantly, there might be observable consequences in the coma. Jets pointing in different directions, asymmetries in dust distribution, or changes in rotational light curve. These are subtle effects requiring careful observation and analysis, but they could provide crucial evidence for or against the more extreme mass loss scenarios. Fourth, and perhaps most important, continued astrometry. Precise position measurements to refine the orbital solution and improve constraints on non-gravitational acceleration. More data points over a longer time frame will reduce the uncertainties in the acceleration parameters. If the acceleration is real and robust, that will become increasingly clear as more measurements accumulate. If it is marginal or potentially artifactual due to measurement uncertainties, that will become apparent too. This is how astronomy works. You make preliminary measurements. You refine them with more data. You gradually converge on robust answers. The current state of debate around the mass loss of 3I Atlas reflects where we are in that process. Early measurements suggesting something interesting, debate about significance and interpretation, and the need for more data to resolve questions. There is also the possibility of discoveries from archived data. When a new object of interest is identified, astronomers often search archives to see if it was inadvertently captured in old images taken for other purposes. Surveys like Pan-STARRS, the Catalina Sky Survey, and others routinely image large portions of the sky. There is a chance 3I Atlas appeared in some of those images before its formal discovery. And if those appearances can be identified and measured, they extend the observational baseline and improve orbit determination. Mining archives is painstaking work, searching through millions of images for a faint moving object that was not the target of the original observations. But for an object as interesting as an interstellar comet, it is worth the effort. We are also waiting on the potential spacecraft tail-crossing data I mentioned earlier. If either Hera or Europa Clipper did traverse the ion tail of 3I Atlas, and if the instruments detected diagnostic signatures, The analysis and publication of those findings will likely take months. This is not a criticism. In situ data analysis is complex and requires careful calibration and interpretation. But it means we could suddenly learn dramatically more about the composition of 3I Atlas later in 2026, or beyond, if those data get analyzed and published. That possibility adds an element of suspense to the story. The investigation might not be over even after the comet itself fades from observability. And then there are the broader questions this comet raises that won't be answered by observing 3I Atlas itself, but by building statistical samples of interstellar objects. How common are comets like 3I Atlas compared to more sedate objects like Borisov? Are most interstellar comets volatile-rich? Or is 3I Atlas unusual even among its peers? Do the observable characteristics of interstellar objects correlate with their incoming velocities or trajectories in ways that might reveal something about their origin regions, like specific star-forming nurseries or ancient stellar populations? These population-level questions require discovering and characterizing many interstellar objects to build meaningful statistics. The Vera Rubin Observatory, expected to begin operations in 2025 and 2026, will revolutionize this field by discovering transient and moving objects at unprecedented rates. Within a few years, we may know of dozens of interstellar. Visitors and 3I Atlas will transition from being a unique curiosity to being one example in a growing catalog. Let me leave you with the unresolved questions that I think are most compelling. The threads we have pulled that have not yet revealed what is at the other end. First, did 3I Atlas lose 10% of its mass, or is that estimate too high? The refined astrometry and continued analysis will eventually constrain this better, but we might remain in a state of uncertainty depending on how much more data gets collected before the comet fades. Second, what is the rotation state of the comet? And does it explain any of the observed activity patterns? We have not had enough continuous monitoring to determine rotation period or axis orientation, and those parameters could reveal whether jets from specific active areas on the nucleus drive the observed behavior. Third, does the complex ion tail structure vary with time in ways that reflect solar wind conditions or intrinsic changes in outgassing? Time domain imaging could answer this if someone commits the telescope resources. Fourth, and most tantalizingly, did those spacecraft fly through the tail and collect direct composition data? That answer might come months from now, or might never come if the data does not exist or goes unanalyzed. This is where I want you to engage with this ongoing story. If you found this investigation compelling, if you are invested in understanding what this interstellar visitor revealed during its brief time in our cosmic neighborhood, then make sure you are positioned to hear about future developments. Hit that subscribe button and turn on notifications so you do not miss follow-up coverage as new data emerges. Drop a comment telling me which aspect of the 3I Atlas story you find most intriguing. The mass loss mystery, the potential spacecraft encounter, the implications for planetary systems, or something else entirely. And share this with anyone you know who appreciates real science at the edge of discovery. Because this is what cutting-edge astronomy looks like. It is not neat and finished. It is ongoing, debated, provisional, gradually converging on truth through careful observation and analysis. We are watching scientific understanding develop in real time, and you are now part of the community following this investigation. 3I Atlas came from another star system, spent a few brief weeks and hours, and is now leaving, never to return. But the questions it raised and the data it provided will keep researchers occupied for years, gradually revealing what this unexpected visitor taught us about the cosmos beyond our sun. That investigation continues, and I will be here to guide you through the discoveries as they emerge. Until then, keep looking up, stay curious, and remember that out there in the darkness between the stars, more visitors are traveling toward their own eventual encounters with our solar system, each one carrying new questions and new answers about the universe we inhabit.